Reality is not a single thread but a tapestry of infinite possibilities. We are about to explore 30 of the most mind-blowing theories physicists have conceived to explain the universe's quantum timelines. This is a journey through the weirdest ideas in science, where every choice might spawn a new cosmos and time itself can twist into loops. By the end, you will see the fabric of existence in a completely new light. We will ask if you are immortal in a parallel world and whether our entire history is just one page in an infinite book. What does it truly mean for something to be real? The first and perhaps most famous of these theories is also one of the most staggering. It suggests that every single decision you make, every quantum event, no matter how small, does not simply resolve itself in our world. Instead, it splits reality in two. This is the many worlds interpretation proposed by a young physicist named Hugh Everett in the 1950s. He offered a radical solution to one of quantum mechanics' greatest puzzles. In the standard view, a particle exists in a blur of all possible states, called a superposition, until it is observed. At that moment, it randomly picks one state to be in, and all the other possibilities vanish. Everett asked a simple, profound question. What if they don't vanish? What if instead the universe itself splits? Every possible outcome of that quantum event actually happens, but each one plays out in its own newly created, fully real branch of reality. Think back to the famous thought experiment of Schrödinger's cat. In the classic version, the cat in the box is both alive and dead until someone looks, a paradox that highlights the weirdness of quantum rules. But in the many worlds view, there is no paradox. When the radioactive atom either decays or does not decay, the universe divides. In one branch, the atom decays, the poison is released, and the cat dies. In the other, newly created branch, the atom remains stable, the poison stays contained, and the cat lives. Both events are equally real. They just happen in separate, parallel universes that no longer interact. This idea scales up from cats to cosmos. Every time you flip a coin, the universe where it lands heads and the universe where it lands tails both come into existence. In one world, you took that job offer across the country. In another, you stayed home. Every possible history, every variation of you that could exist, does exist somewhere in the sprawling multiverse. The implications for free will and destiny are dizzying. You have absolute freedom to choose, but every other version of you makes every other possible choice too. There is no single destiny, only an infinite tree of destinies. Some physicists champion this idea because it elegantly removes the need for a special observer to collapse quantum possibilities. The math works perfectly without adding anything extra. Others find it deeply unsettling, calling it an extravagant waste of realities. Why should the universe multiply itself trillions of times a second just to account for every electron's whim? Yet, if it is true, it means you are, in a sense, immortal. In some branching timeline, every unlikely escape, every fortunate accident has happened for a version of you. The many worlds interpretation paints a picture of reality so vast and prolific that our own lives feel like a single thread in an endless tapestry. A thought that is as humbling as it is exhilarating. But if every choice creates a new universe, what happens to the reality we actually experience? The second theory offers a starkly different answer, one that dominated physics for most of the 20th century. This is the Copenhagen interpretation, named for the city where its architect Niels Bohr worked. Here, there is no branching, no infinite copies. Instead, there is a single, definite reality, but its birth is a moment of profound mystery. According to this view, a quantum particle like an electron does not have a definite position or state until it is measured. It exists in a ghostly blend of all possibilities, a superposition. It is only when an observer makes a measurement, when a conscious mind looks, that this wave of possibilities collapses into one concrete fact. The act of observation itself is what creates reality. The classic demonstration of this is the double-slit experiment. Imagine firing a stream of electrons at a barrier with two narrow slits. If you do not watch which slit each electron goes through, they behave like waves. Each electron passes through both slits at once, creating an interference pattern of light and dark bands on a screen behind the barrier, a telltale sign of wave behavior. But if you place a detector at the slits to observe which path each electron takes, something astonishing happens. The interference pattern vanishes. The electrons suddenly behave like tiny bullets, each going through one slit or the other, and the screen shows two simple clumps. By the mere act of looking, you change the electron's behavior from a spread-out wave to a localized particle. You force the superposition to collapse. This places an enormous, some say strange, importance on the observer. What qualifies as an observation is a camera enough. A cat, a human scientist, the theory is famously vague on this point, leading to deep philosophical puzzles. It suggests that at its most fundamental level, the universe is not a collection of solid objects, but a realm of potentialities. Reality is not something that just is. It is something that happens when it is seen. This makes our cosmos feel less like a clockwork machine and more like a conversation, a dance between the world and the mind. But it also raises a haunting question. If a tree falls in a quantum forest and no one is there to measure it, does it exist in any definite state at all? The Copenhagen interpretation gives us a powerful, if unsettling, picture of a participatory universe, one that sets the stage for even stranger ideas about where our timeline truly resides. The Copenhagen interpretation leaves us with a profound mystery at the heart of observation. But what if the collapse into a single reality isn't caused by a conscious mind at all? A third theory offers a more physical, if no less strange, explanation. It is called quantum decoherence, and it suggests the quantum world vanishes from our view not because we look, but because it cannot help but be seen. Imagine a perfectly balanced coin spinning on its edge. In that blur of motion, it is neither heads nor tails, but a superposition of both states. This is the pristine, isolated quantum system. Now imagine that spinning coin is in a room. Air molecules bump against it. Dust particles settle on its surface. Vibrations from the floor travel up the table. Each tiny interaction steals a little information about the coin's state. Very quickly, the coin tips over, settling definitively as either heads or tails. The superposition is gone. Decoherence is that process of tipping over, but for quantum particles. It proposes that a quantum system, like an electron in two places at once, cannot remain isolated. It constantly interacts with its environment, with stray photons, passing atoms, even the faint pull of gravity. Each interaction effectively measures the system, entangling it with the outside world and forcing it to pick a single classical state. The key insight is that the weird quantum behavior does not actually disappear. From the perspective of the entire entangled system, including the environment, all possibilities still exist in a vast superposition. But for any local observer like us who is only part of that whole, the other branches become inaccessible. They decohere. Information about them leaks out into the universe at large, becoming irretrievably scrambled. This explains why we never see Schrödinger's cat as both alive and dead. The cat itself is a massive object constantly bombarded by air and light. It decoheres almost instantly, forcing the quantum event inside the box to resolve into one outcome long before a human opens the lid. Decoherence acts as a bridge, showing how the definite world of our experience emerges from the fuzzy quantum substrate. It tells us that the boundary between the quantum and classical realms is not about size, but about isolation. A single atom in a perfect vacuum can stay in a superposition for a long time, but connect it to the messy, bustling world, and its quantum nature bleeds away into the environment, leaving behind the solid reality we know. So, while the many worlds theory says all branches are equally real, and Copenhagen says observation picks one, decoherence suggests our classical timeline is simply the one branch we are stuck in, tangled with everything around us. The other possibilities are still out there in the cosmic noise, but we can no longer hear their signal. This leads to a haunting corollary. If our perception of a single reality is just a side effect of being embedded in a noisy environment, what does that say about the true nature of the universe when no one is listening? But what if the strange handoff from quantum possibility to definite fact involves not just the present but the future as well? This brings us to a fourth, deeply unconventional theory. The transactional interpretation proposed by physicist John Cramer in the 1980s suggests that quantum events are not decided by a collapse in the present, but are instead settled through a kind of negotiation across time. In this view, every particle emits not one, but two types of waves into the fabric of spacetime. The first is an ordinary wave moving forward in time called a retarded wave. We are familiar with this, but it also sends out an advanced wave which travels backward in time from the particle's future. These waves are like offers sent out in all directions, past and future. When a particle is about to be measured or interact, these waves seek a match. The advanced wave from a future detection event travels back to the particle's point of origin. The retarded wave from the particle's past travels forward to that same future event. When they meet, they form a closed loop, a handshake across time that confirms the transaction. This handshake is what we perceive as a definite particle taking a specific path. It is as if the universe, before committing to an outcome, sends out feelers to the future to see what possibilities are on the table, then chooses the one that creates a consistent loop. This elegantly explains baffling quantum experiments. Take the double-slit scenario again. According to this theory, the electron does not mysteriously know whether it is being watched. Instead, the future detection event at the screen sends advanced waves back in time. If there is a detector at the slits, the handshake forms there, locking the electron into a particle-like path. If there is no detector, the handshake only completes at the screen, allowing the electron to act as a wave and take all paths at once, creating the interference pattern. The future outcome directly influences the past behavior. This idea of backward causation is its most radical feature. It implies that the timeline of the universe is not a one-way street. Effects can ripple backward to shape their own causes in a self-consistent loop. The present moment is not a solitary decision point, but a nexus where echoes from the future and pulses from the past meet to solidify what we call reality. While controversial and not widely accepted, the transactional interpretation offers a startlingly different lens. It paints a picture of a cosmos in conversation with itself, where every event is a delicate agreement struck across the expanse of time, challenging our deepest assumptions about cause, effect, and the very arrow of reality. While some theories bend time or multiply realities, a fifth idea asks a much simpler question. What if quantum particles are not ghosts at all, but tiny, solid objects with definite positions, just like grains of sand? This is the pilot wave theory, also known as the de Broglie-Bohm theory. It offers a refreshingly clear, if profoundly weird, picture of the quantum world. Forget about superpositions and collapses. In this view, every electron, every photon, has a precise location and trajectory at every single moment. It is always somewhere specific, following a specific path. So what creates all the famous quantum weirdness, like an electron being in two places at once? The answer lies in an invisible guide. Each particle is surfing. Imagine a tiny surfer, the particle itself, riding the crest of a massive, unseen wave. This wave is the quantum wave function, the same mathematical entity from other interpretations, but here it takes on a physical role. It does not represent probability or possibility. It is a real physical wave filling all of space, and it literally pushes the particle around. The surfer does not control the wave. The wave controls the surfer, dictating exactly where it can go. This explains the double-slit experiment with stunning clarity. When you fire electrons one by one at the two slits, the pilot wave passes through both openings. It creates a complex interference pattern on the far side, just like any wave would. Each individual electron, our little surfer, is guided by this wave and travels through only one slit. But because its path is determined by the wave's interference, it ends up landing on the screen in exactly the right spot to build up the overall pattern over time. There is no mystery about which slit it used. It had a definite path all along. This theory restores a comforting sense of realism to the quantum realm. Objects are real with real properties, independent of whether anyone is looking. The need for a conscious observer or a mysterious collapse simply vanishes. The wave function never collapses, it just keeps on waving, eternally guiding particles along their predetermined routes. Yet this elegant solution comes with a monumental price tag, a feature so strange that Albert Einstein himself called it spooky action at a distance. The pilot wave theory is explicitly non-local. The guiding wave connects every particle in the universe instantaneously. If you change something here, the wave updates everywhere at once, faster than light, and every particle riding it feels the change immediately. This violates the classical intuition that nothing can travel faster than light, creating a web of invisible, instantaneous connections tying the cosmos together. So we are left with a trade-off. Do we prefer a universe where particles are fuzzy until observed, or one where they are definite but forever entangled in a faster-than-light dance? The pilot wave theory gives us a clockwork cosmos, but its gears are hidden in a dimension of instant connection, suggesting that the true fabric of reality might be woven with threads that ignore the speed of light entirely. The idea of a single guiding wave connecting every particle hints at a cosmos far more interconnected than we see. But what if that interconnectedness exists on a scale so vast it redefines the word universe entirely? This brings us to the sixth theory, a vision where our entire cosmic history is just a local event within an infinite, bubbling multiverse. It is called eternal inflation, and it paints perhaps the grandest picture of quantum timelines possible. According to this theory, the Big Bang was not a unique beginning. It was more like a bubble forming in a boiling, eternally expanding sea of primordial energy. This sea, known as the inflatoned field, is in a state of constant, exponential expansion, stretching space faster than light. But this expansion is not perfectly smooth. Like any quantum field, it has tiny, random fluctuations. In most regions, the field remains high energy and keeps inflating forever. But in some rare spots, by pure quantum chance, the field's energy drops sharply. When that happens, inflation stops in that localized patch. The tremendous energy of the field is released in a flash, creating matter, radiation, and space itself in a cataclysmic event we would call a Big Bang. Our observable universe is one such bubble within that endless, inflating sea, and we are not alone. The process is eternal. While our bubble universe formed and cooled, the surrounding inflating sea continued to stretch. Other quantum fluctuations in regions now impossibly far away triggered their own bubble universes. This creates a multiverse that resembles a frothing foam, where new bubble universes are constantly nucleating, each with its own separate Big Bang, forever drifting apart in the ever-expanding background. This is where the concept of quantum timelines explodes to a cosmic scale. The random quantum fluctuation that started our bubble was one possibility among infinite others. In another bubble, a slightly different fluctuation occurred, leading to a universe with fundamentally different properties. The strength of gravity, the mass of an electron, the number of spatial dimensions, all the constants we take as fixed laws of nature could be different in other bubbles. Some universes might have physics where stars never form. Others might collapse instantly or be filled with exotic particles we cannot imagine. Our universe, with its specific laws allowing for galaxies, planets, and life, is just one page in an infinite book of realities. In this view, the quantum timeline of our entire cosmos is not a solitary thread but one strand in an endless tapestry of cosmic histories. Every possible variation of physical law, every alternate beginning, likely exists somewhere in the multiversal foam. This means the deepest questions about why our universe is the way it is, why the constants are so finely tuned for complexity, might have a simple, if humbling, answer. We do not live in a special universe. We live in one that, by sheer statistical chance in an infinite ensemble, had the right conditions for us to be here to ask the question. Eternal inflation takes the quantum idea of multiple possibilities and projects it onto the canvas of all existence, suggesting that the ultimate timeline is not a line at all, but an ever-branching, unbounded tree of entire cosmoses. If our universe is just one bubble in an eternal foam, what is the fundamental nature of the space it occupies? A seventh theory proposes an answer so radical it redefines the very concept of reality. This is the holographic principle, and it suggests that everything we perceive in 3 dimensions, including the flow of time, might be a grand illusion projected from a 2-dimensional surface. The idea emerges from a deep puzzle about black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, a measure of its hidden information, is not proportional to its volume as you might expect. Instead, it is proportional to the area of its event horizon, the spherical surface that marks its point of no return. This was strange. In our everyday world, the information needed to describe the contents of a box grows with the box volume. But for a black hole, the ultimate container, the maximum information it can hold is dictated by its surface area. It is as if all the data about every star, planet, and atom that ever fell in is not stored inside the 3-dimensional hole, but is somehow painted pixel by pixel onto its 2-dimensional boundary. This led theorists like Gerard T. Hooft and Leonard Susskind to a staggering hypothesis. What if this is not a quirk of black holes but a fundamental law of the universe? What if all the information within any region of space, including our entire cosmos, is actually encoded on its outer surface? In this view, our rich 3-dimensional reality, with its galaxies, mountains, and people, is akin to a hologram. A hologram is a 2-dimensional piece of film that, when illuminated with laser light, projects a stunningly realistic 3-dimensional image. The holographic principle suggests our universe works the same way. The true, fundamental reality is a vast, shimmering 2-dimensional surface at the edge of space, perhaps at the cosmic horizon where light from the Big Bang first reaches us. Every event, every particle, every moment of history in our 3-dimensional world is just a translation of data written on that distant, flat screen. This has profound implications for our understanding of time. If our 3-dimensional reality is a projection, then time itself might not be a fundamental ingredient of the universe. It could be an emergent property like temperature emerging from the motion of atoms. On the 2-dimensional boundary, there may be no time as we know it, just a vast static arrangement of information like the data on a cosmic DVD. Our experience of a flowing timeline from past to future would be generated as that data is decoded into the 3-dimensional movie we call the present. This perspective offers a potential path to uniting quantum mechanics and gravity, the holy grail of modern physics. The messy quantum interactions could be perfectly described by a simpler, gravity-free theory living on the 2-dimensional boundary. Our complex 4-dimensional spacetime with gravity would then be a projected shadow of that simpler reality. So, consider your own life, your memories, your sense of a past flowing into a future. The holographic principle invites us to ponder a dizzying possibility. Your entire timeline from birth to this very moment might not be a thread moving through time, but a static pattern of information eternally written on the edge of everything. We are not travelers through time, we are a frozen sculpture, and our consciousness is a light reading it in sequence, mistaking the scan for a journey. The holographic universe challenges our deepest intuitions about space and time. But what if we could peer even deeper past the illusion of smooth spacetime to see the very threads that weave it together? This is the promise of loop quantum gravity, a theory that dares to dismantle the stage upon which all other physics plays out. Its goal is monumental: to finally unite Einstein's theory of general relativity, which describes gravity as the curvature of spacetime, with the chaotic rules of quantum mechanics. The result is a vision of reality not as a continuous fabric but as a tapestry of indivisible stitches. In this theory, space itself is not smooth and infinitely divisible. It is quantized, woven from tiny, vibrating loops of gravitational field, each about 1 trillion times smaller than an atomic nucleus. Picture the universe not as a blank sheet, but as an unimaginably fine mesh, a network of these fundamental loops intersecting at nodes. Where the loops join, you get a grain of space, an elementary volume. Where they link, you have an area. There is no such thing as an arbitrarily small distance or volume. Space comes in discrete, tiny packets like the pixels on a screen. This has a stunning consequence for the history of our cosmos. In Einstein's equations, if you rewind the expansion of the universe, you reach a point of infinite density and temperature called the Big Bang singularity, a place where the laws of physics break down entirely. Loop quantum gravity offers a dramatic escape. Because space is granular, it cannot be compressed to a point of zero volume. Instead, as you rewind toward the Big Bang, the density reaches a maximum, and then quantum gravity effects become repulsive. The collapse reverses. The universe undergoes a quantum bounce. Our Big Bang was not the absolute beginning, but the moment our universe rebounded from a previous cosmic phase of contraction. We may live in a cyclical cosmos with no true start or end, only an endless sequence of bounces. This idea of a woven spacetime also opens doors to profound structural possibilities. Just as threads in a fabric can be knotted or braided, the loops of quantum gravity could tangle in ways that change the topology of reality itself. These loops might theoretically connect distant regions in unexpected manners, or even link different timelines or branches of the universe in a fundamental way. The fabric of reality could have tiers that are mended or tunnels that are stitched closed, all at this unimaginably small scale. It suggests a universe that is not a static container, but a dynamic, evolving network, capable of changing its very shape and connectivity through cosmic cycles. While still a developing theory, loop quantum gravity gives us a powerful new metaphor. Reality is not a stage. It is the intricate quantum lacework of the stage itself, forever vibrating, potentially bouncing, and perhaps holding within its loops the secret passages to every corner of existence. The idea of a woven spacetime leads to an even more profound question. What are the threads themselves made of? This brings us to a ninth theory, one of the most ambitious frameworks in all of physics. String theory proposes that at the very heart of reality, there are no point-like particles. Instead, the fundamental ingredients of the universe are unimaginably tiny, vibrating loops of energy. Think of a guitar string, pluck it, and it vibrates at a specific frequency to produce a musical note. In string theory, every elementary particle is a string vibrating in a particular pattern. One vibration mode corresponds to an electron. A different, higher energy vibration creates a quark. The force-carrying particles, like the photon for light or the graviton for gravity, are other notes on the same cosmic instrument. The music of these strings, in all its harmonic complexity, composes everything we see. But there is a catch. For the mathematics of this beautiful symphony to work, these strings cannot simply vibrate in our familiar 3 dimensions of space and one of time. They require more room. String theory demands the existence of extra, hidden dimensions of space, curled up so tightly that they are a billion times smaller than an atom. To visualize this, picture a garden hose. From a great distance, it looks like a simple one-dimensional line, but up close, you see it has a circular dimension wrapped around its length. A tiny ant walking on the hose could move along its long axis, or it could take a short trip around its circumference. Our universe might be similar. We experience the three large, expansive dimensions, but at every point in space, there could be 6 or 7 extra dimensions curled into intricate, microscopic shapes. These shapes are not random. They are called Calabi-Yau manifolds, complex geometric forms that determine how the strings vibrate within them. And here is where the concept of quantum timelines explodes into a new landscape, quite literally. The specific way these extra dimensions are folded dictates the vibrational patterns of the strings, which in turn sets the laws of physics for that universe. The mass of an electron, the strength of gravity, the number of particle families all emerge from the geometry of this hidden realm. String theory does not predict one unique shape. It suggests a vast number of possibilities, perhaps 10 to the 500 or more. This is the string theory landscape, a cosmic archipelago of possible universes, each with its own compactified geometry and therefore its own unique set of physical laws. Our universe, with its specific constants, would be just one island in this incomprehensibly vast ensemble. This leads to a breathtaking speculation. Could these hidden, folded dimensions do more than just define our local laws? Could they act as bridges or contain entire realities separate from our own? If a dimension is compactified, it is a tiny loop. But what if, in another branch of the multiverse or another bubble in eternal inflation, a dimension failed to curl up? What if it remained open and expansive? That universe would have a fundamentally different structure of spacetime. It is conceivable that within the full, higher dimensional bulk of reality predicted by string theory, these disparate universes could, in principle, touch or interact along these extra-dimensional directions. Entire alternate histories with different timelines and physical rules might not be infinitely far away in some parallel branch. They could be literally folded away in dimensions we cannot perceive, separated from us by a gap as small as it is unbridgeable with our current understanding. Our entire cosmic timeline might be one sheet in a multidimensional stack, forever feeling its own vibrations but deaf to the symphonies playing on the pages above and below. The intricate geometry of string theory suggests hidden connections between possible realities. But what if, instead of branching into new timelines, the universe possesses a stubborn, unbreakable consistency that prevents any true change to history? This is the 10th theory, the Novikov self-consistency principle, and it offers a radical solution to the most famous problem with time travel, the paradox. Imagine going back in time to prevent your own birth. If you succeed, you would never exist to go back in time, so you could not have prevented it. This logical contradiction seems to make time travel impossible. The Novikov principle, proposed by Russian physicist Igor Novikov, cuts this knot with a simple, elegant rule. The universe is consistent. Any actions taken by a time traveler were always part of history. There is only one timeline, and it is fixed, free of paradoxes because it already accounts for the traveler's interference. Think of a billiard ball rolling toward a wormhole that leads back to a moment just before it entered. The ball goes through the wormhole and emerges in the past, flying out to strike its earlier self, knocking it off course. But here is the key: the earlier self's altered path is precisely what sends it perfectly into the wormhole in the first place. The knock was not an interruption. It was always the necessary nudge that created the very event it seemed to disrupt. The timeline is a single, closed loop, perfectly self-fulfilling. Apply this to a human traveler. You go back to see a famous historical speech. In the crowd, you accidentally trip, causing a commotion that distracts the speaker and makes them pause at a crucial moment. That pause becomes the iconic, dramatic hesitation remembered in all the history books. Your attempt to observe history was always part of that history. You did not change anything, you completed it. This principle transforms time from a river you can divert into a Möbius strip, a loop with only one side. Every event, including those caused by time travelers, is locked in place. The implications for free will and destiny are profound. If this principle governs reality, then the entire cosmic script, from the Big Bang to the last star's flicker, is predetermined and unchangeable. Your choices feel real to you, but they are the only choices you could ever have made, woven into the fabric of a single, self-consistent timeline. In a quantum context, this adds another layer. Perhaps the universe does not resolve quantum possibilities by branching or collapsing. Perhaps it simply selects the one outcome that maintains global consistency across all of time, avoiding any paradox. Your life, with all its apparent chance and decision, would then be a single, immutable thread in a tapestry that was finished before it began. It is a vision of cosmic fate, where every quantum event and every human thought is a note in a symphony that has already been played, leaving us to simply discover the melody as we move through it. While the Novikov principle locks us into a single, unchangeable script, another theory proposes that the real branching happens not in the cosmos, but within the theater of our own mind. The many minds interpretation takes the puzzle of observation and turns it inward, suggesting that when a quantum event has multiple possible outcomes, it is not the universe that splits. It is your consciousness that divides. In this view, the wave function never collapses. The physical world remains in a single, sprawling superposition of all possibilities. But the mind of any observer does not perceive this unified blur. Instead, it fractures into multiple, separate streams of awareness, each one becoming conscious of just one of the possible outcomes. Imagine you are about to look at the result of a quantum experiment, one where an electron could be measured as spinning either up or down. According to this theory, at the moment of observation, your single, unified consciousness branches. One stream of you becomes aware of the electron spinning up. Another, completely separate stream of you becomes aware of it spinning down. Both experiences are equally real, but they are now isolated from each other. There is no single universe splitting into copies. There is one quantum reality containing all possibilities, populated by a multitude of branching minds, each living in its own perceived timeline. This makes the multiverse a profoundly intimate, internal phenomenon. Every possible history unfolds in the external world, but you only experience one thread at a time because your awareness continually forks at every ambiguous quantum junction. The friend who reports seeing the opposite result from you is not in a parallel universe. They are simply another mind branch, experiencing a different facet of the same superposition you both inhabit. This idea finds a strange resonance with certain speculative theories about consciousness itself. Some researchers, like Roger Penrose, have proposed that consciousness might not be a byproduct of classical brain activity, but a quantum process occurring within the brain's neural structures. If that were true, then the branching of mind states could have a physical correlate in the quantum mechanics of our own biology. The many minds interpretation also touches on philosophy's hard problem of consciousness, the question of why and how physical processes in the brain give rise to subjective experience. This theory offers a stark answer. Our experience is not a single, continuous narrative generated by a brain. It is one thread among many, a temporary branch in a tree of possible awarenesses growing from a single quantum source. The implication is both liberating and lonely. You are immortal in a sense because for every quantum accident that could end your life, there is a branch of your mind that experiences survival. But you are also perpetually splintering, losing connection with countless other versions of your own awareness at every moment. Your reality is not a shared stage, but a private screening of one film from a library containing every possible edit. This places the ultimate mystery of the timeline squarely within us, suggesting that the flow of time and the solidity of the world are not features of the cosmos, but artifacts of a consciousness forever dividing to navigate an ocean of possibilities. This splintering of awareness leads to one of the most startling and personal thought experiments in all of physics. It is called quantum immortality, and it proposes that from your own subjective point of view, you might be impossible to kill. This idea emerges directly from the many worlds interpretation. If every possible outcome of a quantum event occurs in some branch of reality, then there is always a branch where you survive, no matter how improbable that survival may be. Consider a grim game of quantum Russian roulette. A gun is pointed at your head, but its trigger is linked to a quantum random number generator. There is a 50% chance it will fire. You pull the trigger. In one branching universe, the quantum number results in a firing pin strike, and that version of you dies instantly. But in another, equally real branch, the number results in a harmless click. Your conscious experience cannot continue in the branch where you die. By definition, death is the end of subjective awareness. Therefore, the only experience you can ever have is the one in which you survive. From your first-person perspective, you will always hear the click. You will always find yourself in the timeline where the improbable escape happens. This logic scales to any life-threatening probabilistic event. A collapsing building, a terminal illness, even old age. There will always be some vanishingly small branch of the multiverse where a quantum fluctuation alters the event just enough for you to live a moment longer. Your consciousness, argues this thought experiment, will inevitably follow that branching path. You would become a perpetual survivor, hopping from one timeline to the next, always landing in the reality where you continue to exist. The implications are deeply existential. It suggests a form of functional immortality, but a profoundly lonely and strange one. You would watch as friends and loved ones seemingly die around you, though from their perspective, they continue in branches where they survive. The world would gradually become alien as you outlive your species, your planet, and even the stars themselves, always finding yourself in the one cosmic timeline where conditions, against all odds, permit your continued consciousness. This is not a theory anyone can prove, and its counterarguments are strong. Critics point out that consciousness likely requires a functioning brain, and there is a limit to how many quantum miracles could preserve that complex structure indefinitely. Eventually, all possible branches might lead to states incompatible with any form of coherent experience. Furthermore, this idea confuses probability with guarantee. While a surviving branch always exists, the overwhelming majority of branches contain your death. From an objective, God's eye view of the multiverse, you are almost certainly dead. The eerie conclusion is that quantum immortality is not about true immortality, but about the bizarre nature of first-person experience in an infinite multiverse. It highlights that what we call our reality is not a random sample of the cosmos, but a profoundly biased one, filtered by the simple tautological fact that we are here to observe it. It forces us to ask a haunting question: are we the authors of our fate, or are we merely the audience, forever seated in the one theater where the show never ends? The unsettling thought of subjective immortality forces us to confront the nature of time itself. Is it a river we sail, or is the entire journey already mapped? Theory 13 offers a definitive, if static, answer. This is the block universe, also known as eternalism. It proposes that past, present, and future are not sequential. They all exist permanently and equally, laid out together in a single, four-dimensional structure. Time, in this view, is just another dimension of reality, much like length, width, and height. Think of a movie on a DVD. The entire story is there, encoded on the disc all at once. Your experience of watching it, from opening scene to credits, is like your consciousness moving through the timeline of the block. But the scenes themselves, the beginning, the middle, the end, they all coexist on the disc. The block universe is that disk for all of reality. Your birth, your reading of this sentence, and every moment to come are all fixed points in this grand, unchanging sculpture of spacetime. This idea finds strong support in Einstein's theory of relativity. A key insight of relativity is that there is no universal now. What you perceive as the present moment depends on how you are moving through space. Two events that are simultaneous for a stationary observer might happen at different times for someone moving at high speed. Since there is no privileged frame of reference to define a single present, it makes sense to treat all moments from all perspectives as equally real. They are all just different coordinates in the four-dimensional block. In this framework, your life is not a path you are carving. It is a world line, a fixed, thread-like structure weaving from your birth coordinate to your death coordinate. Every decision, every action is an eternal feature of this line. Free will, from this perspective, becomes a profound illusion of consciousness, a feeling generated as we encounter each pre-existing moment. This has a direct and startling implication for our quantum timelines. If the entire block is fixed, then what does quantum probability even mean? Where is the room for possibilities and alternate outcomes? One interpretation is that probability is an artifact of our limited internal view. From inside the block, we lack the information to know which path our world line will take, so we assign probabilities. But from a God's eye view outside the block, the path is singular and determined. There is no branching, only one intricate line. Yet another, more radical possibility emerges from marrying the block universe with quantum mechanics. Perhaps the block is not singular. Perhaps every quantum possibility generates its own complete four-dimensional block. In this vision, the multiverse is not a tree of branching lines, but a stack of complete static universes, each a different version of the total spacetime history. Your world line in one block shows you taking the left turn. In another, otherwise identical block, your world line shows you taking the right. Superposition, then, would not be a blur of possibilities in one timeline, but the simultaneous existence of multiple, complete blocks. We experience only one, but the others are just as real, eternally sitting alongside ours in a higher dimensional stack. The block universe model is both elegant and existentially challenging. It removes the mystery of a flowing time, but at the cost of making our lived experience of change and choice feel like a magnificent, persistent dream. It asks us to consider that our deepest feeling, the relentless march of the present, might be the ultimate illusion, and that every moment of joy, sorrow, and discovery is already out there, forever inscribed in the cosmic stone. The block universe presents time as a frozen sculpture, but what if the connections within it are not just static but can also run backward? This 14th idea, retrocausality, turns our everyday logic on its head by proposing that the future can reach back and influence the past. It suggests that at the quantum level, the arrow of time might be more of a suggestion than an iron law. One of the most compelling pieces of evidence for this comes from a classic thought experiment made real, the delayed choice quantum eraser. Imagine sending a single photon toward a beam splitter, a device that can let it pass through or reflect it, creating two possible paths. These paths can later be recombined to create an interference pattern, a signature that the photon behaved as a wave, taking both paths simultaneously. Now add a twist. After the photon has already passed the beam splitter and is in flight, but before it hits the final detector, you randomly choose whether to insert a device that will determine which path it took. Astonishingly, the photon's behavior seems to change retroactively. If you choose to measure its path, it acts like a particle that took one definite route. If you choose not to measure, it acts like a wave that took both. The decision you make in the present appears to rewrite the history of the photon, determining what it was doing in the past. It is as if the photon, in its past, knew what kind of experiment it would encounter in its future and adjusted its behavior accordingly. This is not magic, it is a direct prediction of quantum mechanics. The physicist John Wheeler, who devised this experiment, saw it as proof that no quantum phenomenon is truly a phenomenon until it is registered by an irreversible act of observation. The past has no definite shape until the future gives it one. An even more foundational retrocausal theory is the Wheeler-Feynman absorber theory. Proposed in the 1940s, it sought to solve a puzzle about how charged particles like electrons radiate light. Their idea was that an electron shaking in the present does not simply send radiation out into the void. Instead, it sends waves both forward and backward in time. The forward wave travels to the future where it is absorbed by other particles. Those particles then send an identical wave backward in time, perfectly converging on the original electron at the moment it started shaking. The radiation we see is the result of this handshake across time. The future absorption is necessary for the past emission to occur at all. While developed for classical electrodynamics, this idea of a two-way dialogue between past and future perfectly sets the stage for quantum retrocausality. The implication is that causes and effects can form a closed loop where the effect is part of the reason the cause happened. At the quantum scale, this could mean a particle's state is not determined by its past alone, but also by what measurement will be performed on it later. Its history is contingent on its future. This weaves timelines into a non-linear tapestry where events are not linked in a simple chain but in a web of mutual influence. If true, even in a subtle way, it suggests our present reality is not being pushed solely from behind by the past. It is also being pulled gently but surely by the gravitational pull of potential futures. The choices we have not yet made, the observations we have not yet performed, could be whispering back along the threads of time, helping to nudge the quantum dice just enough to make a consistent story. Our lives may be a constant negotiation between the echoes of what was and the shadows of what might be. The notion of a future whispering to the past hints at a universe governed by rules, perhaps even programmed ones. If reality is quantized and events can be retroactively influenced, could these be signatures of something far more engineered? This leads us to the 15th theory, a modern idea that has leapt from philosophy and science fiction into serious scientific discourse. It is the simulation hypothesis, and it proposes that our entire universe, with all its quantum timelines, is not a fundamental reality but a digital construct, a simulation running on some unfathomably advanced computer. The core argument begins with the very nature of physics we have been exploring. Our reality appears to be pixelated. Space has a minimum possible length, the Planck length. Time has a minimum tick, the Planck time. Energy comes in discrete packets called quanta. This is exactly how a digital simulation works, with a finite resolution to save processing power. Those strange quantum effects like superposition and entanglement could be clever programming shortcuts. Instead of rendering every single particle in a definite state at all times, which would be computationally prohibitive, the simulation only calculates a particle's precise properties when it is being observed, a trick called lazy evaluation. The infamous double-slit experiment, where particles behave as waves until measured, could be the simulation optimizing its resources, only committing to a specific outcome when the data is requested by a user or by another part of the code. From this perspective, the many worlds of quantum mechanics take on a new meaning. Different timelines might not be parallel physical universes. They could be separate simulation instances like multiple saves of a video game. An advanced civilization might run countless iterations of a cosmic history, tweaking initial conditions to see different outcomes. Our specific universe would be just one run in a vast archive of simulated realities. The concept of quantum immortality finds a chillingly logical explanation here. If your consciousness is data within the simulation, and the program is designed to maintain continuity of experience, It would simply load your point of view into the next viable branch whenever a terminal event occurs in your current one. You would always find yourself in the instance where you survive because the other instances are no longer being rendered for your awareness. Even the idea of retrocausality fits. In a simulation, the entire timeline exists as code. A programmer or a higher-level process could easily adjust a variable in the past based on an outcome in the future, creating the appearance of backward-in-time influence. This raises the provocative possibility of glitches. If we are in a simulation, then rare quantum anomalies or statistical outliers might not be random flukes. They could be minor bugs in the code or even intentional cheat codes left by the programmers. Some theorists speculate that phenomena like quantum tunneling, where a particle passes through an energy barrier it classically shouldn't, could be such a glitch, a momentary lapse in the physics engine. The ultimate multiverse, then, might not be a frothing sea of inflating bubbles, but a cosmic server farm running countless simulations in parallel. Each quantum branch is a separate process thread, and the superposition we measure is simply the program checking multiple possibilities before deciding which one to display locally. This idea, while speculative, forces a profound shift in perspective. It asks us to consider that the deepest laws of physics are not laws of nature, but the source code of reality, and that every choice we make might be exploring a different path in a grand, digital labyrinth designed by minds we cannot even comprehend. If our reality is a simulation, the programmers would have chosen specific settings. But if it is not, why do the fundamental laws of our universe seem so perfectly tailored for our existence? This is the puzzle addressed by the 16th theory, the anthropic principle. It is not a mechanism like a branching timeline, but a powerful logical lens through which to view our place in the cosmos. At its simplest, the anthropic principle states that we must be prepared to take into account the fact that our very existence as observers imposes a selection effect on the kind of universe we can possibly see. We observe a universe compatible with observers because we are here to observe it. This seems almost tautological, but its implications are world-shaking when applied to the fine-tuning problem. Physicists have discovered that many of the fundamental constants of nature, like the strength of gravity or the mass of the electron, appear exquisitely balanced on a knife's edge. If any of these values were altered by even a tiny fraction, the universe would be sterile. Stars would not form, atoms would not hold together, and complex chemistry, the basis for life, would be impossible. It seems as if the cosmos was designed for life. The anthropic principle offers a different, less mystical explanation, one that leans heavily on the concept of countless failed timelines. The weak anthropic principle is the more conservative version. It simply notes that our location in the universe, both in space and time, must be compatible with our existence as observers. We could not find ourselves in the empty void between galaxies a billion years after the last star has died, because such a place and time could not support us. Our observations are necessarily biased by our own prerequisites for life. This is a statement about our specific cosmic address, not the universe as a whole. The strong anthropic principle takes a much bolder leap. It suggests that the universe must have properties that allow life to develop at some stage in its history. This version often dovetails with the multiverse concepts we have explored. In a landscape of infinite universes, such as those generated by eternal inflation or the string theory landscape, every possible combination of physical constants is realized somewhere. The overwhelming majority of these universes are stillborn, dark, or chaotic, utterly inhospitable to any form of complexity. But by sheer chance, a tiny fraction will have the precise, improbable combination of constants that permits stars, planets, and life. We, of course, can only find ourselves in one of those rare, habitable bubbles. Our universe is not special because it was designed for us. It is simply the one lottery ticket out of an infinite pile of losers that happen to have the winning numbers for life. This perspective reframes fine-tuning from a miracle into a statistical inevitability. The countless failed universes, the silent and dark timelines where physics forbids existence, are the necessary background against which our single, shining possibility emerges. We are not the purpose of the cosmos, but a rare and fascinating accident within an unimaginably vast ensemble of cosmic experiments. The debate, however, is far from settled. Critics argue that the strong anthropic principle is an untestable retreat from explanation, a clever way of saying we got lucky. Proponents counter that it is the most natural conclusion from combining modern cosmology with the undeniable fact of our existence. It uses the very concept of a multiverse with its infinite quantum timelines to answer the oldest question of all: why is there something rather than nothing, and why does that something look like this? The answer may be that for every timeline like ours, there are an infinity of silent ones, and we are simply the echo that learned to listen. The eerie silence of all those failed universes brings us back to our own and to a pressing question. How does the single, shared reality we all experience actually emerge from the quantum soup of possibilities? A 17th theory offers a compelling answer by borrowing a famous idea from biology. It is called quantum Darwinism, and it proposes that our classical world is shaped by a process akin to natural selection, where only the fittest quantum information survives to be seen. At its heart is the mechanism we touched on earlier, decoherence. When a quantum system interacts with its environment, its fragile superposition breaks down. But quantum Darwinism goes further, asking what happens to the information about the system after it decoheres. The answer is that it gets copied over and over again and broadcast out into the world. Think of a tree falling in a forest. It does not create a single private sound wave. It generates countless vibrations that travel through the air, bounce off leaves, and rustle the grass. Each of these interactions carries a copy of the same information: that a tree fell. In the quantum realm, something similar happens. When you measure an electron spin, the result is not just registered in your detector. That piece of information is redundantly imprinted onto the countless photons, air molecules, and other particles that scatter from the interaction. These copies proliferate, spreading through the environment like ripples. This redundancy is key. It makes the information robust and accessible. Any observer who comes along can sample just a small part of the environment, a few of those ripples, and still deduce the original fact that the electron spin was up. The quantum state that gets copied most effectively, that leaves the clearest and most numerous imprints, is the one that becomes objective. It is the one we all agree on. This is the Darwinian part. In the environment's chaotic sea, only certain quantum states are stable enough to be faithfully replicated. Others are fragile and get scrambled beyond recognition. The states that can survive this process of environmental interaction and copying are the ones that are naturally selected to form our classical reality. They are the fittest. Now apply this to the concept of timelines. In the vast quantum multiverse, countless potential histories are constantly bubbling up. But most are ephemeral, decohering into incoherent noise almost instantly. Quantum Darwinism suggests that the timeline we perceive, the one that feels solid and shared, is the one where a consistent set of quantum states manage to get massively copied and broadcast. It is the narrative that successfully reproduced itself into the environment, creating a consensus among all observers who sample that environment. Your memory of yesterday, the data in a history book, the light from ancient stars reaching us today, these are all redundant records of a selected quantum history. They are the echoes that survived. This theory elegantly bridges the gap between the weird quantum underworld and the stable stage of our daily lives. It tells us that objectivity is not a fundamental property, but an emergent one, born from a relentless process of information replication. The world we agree upon is not the only possible world. It is simply the one whose story was told most loudly and clearly. its signal amplified by the very fabric of reality until it became the only story we could all hear. Quantum Darwinism shows how a shared reality is selected from the quantum noise. But what if that noise is not just informational static, but the very fabric of spacetime being stitched together? This brings us to a breathtaking 18th theory, one that forges a direct link between the weirdest features of quantum mechanics and the most dramatic structures in general relativity. It is the ER equals EPR conjecture, and it proposes that two of Einstein's most famous ideas are in fact two sides of the same cosmic coin. On one side you have EPR, named for Einstein, Podolsky, and Rosen. Their famous 1935 paper highlighted the strangeness of quantum entanglement, where two particles become so deeply linked that measuring one instantly determines the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, a violation of local realism that troubled him deeply. On the other side, you have ER, the Einstein-Rosen bridge. This is the formal name for a wormhole, a theoretical tunnel through spacetime that could, in principle, connect two distant regions of the universe or even different universes entirely. For decades, these were seen as separate, unrelated concepts. One was a bizarre quantum connection with no physical bridge. The other was a geometric structure in spacetime, often considered unstable and untraversable. Then, in 2013, physicists Juan Maldacena and Leonard Susskind made a radical proposal. What if entanglement and wormholes are not just similar? What if they are exactly the same thing described in different languages? The ER equals EPR conjecture suggests that every pair of entangled particles is not mysteriously linked across empty space. They are, in fact, connected by an incredibly tiny Planck-scale wormhole. This wormhole is not a tunnel you could travel through. It is a geometric manifestation of the quantum link itself, stitching the particles together through the fabric of spacetime. Think of two friends living on opposite sides of a vast mountain range. From their perspective, they are far apart and can only communicate instantly by some mysterious, spooky telephone. But from a God's eye view, there is a hidden tunnel running straight through the mountain, connecting their homes. The instant communication is not magic, it is just a shortcut. The conjecture proposes that quantum entanglement is that shortcut written into the geometry of reality. This idea transforms our picture of the quantum vacuum. Empty space is not truly empty. It is a seething quantum foam, and at the tiniest scales, it might be threaded with an unimaginably dense network of these microscopic wormholes, each one representing an entanglement between virtual particles popping in and out of existence. Spacetime itself may be woven from this web of quantum connections. Now, let us speculate wildly, as the theory invites us to do. If every entanglement is a tiny wormhole, could we somehow strengthen that connection, inflate the wormhole, and make it traversable? Some theoretical work suggests that by adding enough energy or by creating the right kind of quantum entanglement between large collections of particles, one might stabilize a microscopic wormhole, potentially opening a gateway. This is purely speculative, but it points to a staggering possibility. The quantum links that enable instant communication of information might, under extreme conditions, become tunnels for physical travel. This leads to the most profound speculation of all. If the fabric of reality is a network of entanglements, and each entanglement is a wormhole, then the entire quantum multiverse might be a single, massively interconnected structure. Different branches of the wave function, alternate timelines, even separate bubble universes in eternal inflation, might not be infinitely far apart in some abstract sense. They could be adjacent territories in a higher dimensional landscape connected by a labyrinth of quantum wormholes. Every choice that creates a new branch might also spin off a new connection in this cosmic web. In such a reality, every timeline is just a click away through a quantum wormhole, if only we knew how to navigate the map. This vision unifies the greatest puzzles in physics. It suggests that the non-locality of quantum mechanics and the geometry of gravity are parts of a single, deeper truth. The spooky action at a distance that troubled Einstein might simply be the universe taking a shortcut through its own folded interior, a hidden geography where every entangled pair holds the blueprint for a bridge. Stephen Hawking looked at the dizzying possibilities of wormholes and time loops and proposed a cosmic safety mechanism. He called it the chronology protection conjecture, a principle suggesting the laws of physics conspire to prevent time travel to the past, not as an accident but as a necessary defense. Hawking argued that the universe seems to have a deep allergy to paradoxes, and it will actively sabotage any attempt to create one. The proposed mechanism for this sabotage comes from the quantum realm itself. Imagine trying to stabilize a wormhole to make it traversable for a time machine. As you manipulate the exotic matter and energies involved, you would inevitably create a region of spacetime where time loops back on itself, a closed time-like curve. In such a region, an event could be both the cause and effect of itself, the very definition of a paradox. Hawking proposed that in this unstable environment, quantum vacuum fluctuations, the tiny particles that pop in and out of existence everywhere, would run amok. A single photon, for example, could travel around the time loop an infinite number of times. Each time around, it would add its energy to the loop. The energy would build and build without limit, creating a feedback loop of infinite energy density that would rip the wormhole apart or collapse it into a singularity long before anyone could send a message, let alone a person, through it. The universe would rather destroy the gateway than allow a contradiction to be woven into its fabric. This idea frames the linearity of our timeline not as a default setting, but as a fiercely protected condition. It suggests that the smooth flow from past to future is not just how things are, but how they must be to avoid catastrophic instability. The conjecture sparks a fierce debate, however. Is chronology protection a fundamental, unbreakable law woven into the heart of quantum gravity, or is it merely a limitation of our current, incomplete theories? Some physicists argue it is an elegant solution to a profound problem. A law that ensures causality remains the bedrock of reality. Others see it as a temporary barrier, a sign that we do not yet understand how to properly engineer spacetime. They point out that the equations of general relativity do allow for closed time-like curves in certain exotic scenarios. Perhaps with a sufficiently advanced understanding, one could carefully tune the conditions to avoid the runaway quantum effects, like a master engineer damping vibrations in a bridge. If the conjecture holds, it paints a universe that is inherently self-consistent, where the quantum timeline is a single, robust thread guarded by its own laws. If it falls, it opens the door to a cosmos where time is malleable and history is a substance that can be revisited, with all the terrifying and wondrous possibilities that entails. Hawking's idea ultimately asks us whether the flow of time is a gentle current or a fortified wall, and whether the universe is preserving our history or simply waiting for us to learn how to navigate its folds. Hawking's cosmic safety mechanism protects the linear flow of time we know, yet the very fabric of that time, the stage upon which all events play out, might be built on a foundation far more fluid and precarious than we suspect. This brings us to the 20th theory, a perspective that emerges not from cosmology, but from the bedrock rules of particle physics itself. It is the multiverse of quantum field theory. To understand it, we must first reshape our view of reality's most basic ingredients. Forget thinking of the universe as filled with separate, tiny particles like electrons and quarks. Instead, picture an infinite, invisible ocean filling all of space. This ocean is not made of water, but of abstract entities called quantum fields. There is an electron field, a quark field, a photon field, one for every type of fundamental particle. These fields are everywhere at every point, even in what we call empty space. A particle, then, is not a solitary speck. it is a localized ripple and excitation in its corresponding field. An electron is a tiny knot of energy in the universal electron field. A photon is a vibration in the electromagnetic field. Everything that exists is just a pattern of waves dancing on this vast, interconnected sea of fields. Now, the properties of these fields, like their energy, are not always flat and calm. Think of a landscape of hills and valleys. The lowest possible energy state for a field is called its vacuum state, the true bottom of a valley. But here is where things get strange. The shape of this landscape, the arrangement of hills and valleys, is determined by something called symmetry. In a perfectly symmetric state, all directions are equal, like the peak of a round hill. But such a state is often unstable. A famous analogy is a ball balanced perfectly on the tip of a cone. It is symmetric, but the slightest nudge will send it rolling down into a specific groove, breaking that symmetry. In physics, this is spontaneous symmetry breaking. The field settles into a specific, stable valley, but that valley is just one of many possible ones it could have chosen. This choice has monumental consequences because it sets the laws of physics for that region of space. The masses of particles, the forces between them, even the number of dimensions that feel expansive, can all be determined by which valley, which vacuum state the fields settle into. This leads to a staggering possibility. Different regions of the primordial universe, or different bubbles in an inflating multiverse, could have had their quantum fields settle into different vacuum states. Each one would represent a universe with completely different fundamental laws. In one valley, electrons might be heavy and gravity strong. In another, atoms might never form. Our universe, with its specific particle masses and forces, is simply the one where the fields fell into a particular set of valleys that allowed for complexity and life. The multiverse here is not just a collection of similar universes with different histories, but a landscape of fundamentally different realities, each with its own physics, born from the random settling of quantum fields. This framework contains a profound and unsettling implication for our own future, centered on the concept of the false vacuum. What if our universe's vacuum state, the valley our fields sit in, is not the absolute lowest valley on the landscape? What if it is a false vacuum, a relatively stable depression, but with a much deeper, truer vacuum lying far below it? Our entire cosmos would be in a metastable state, like a ball resting in a shallow bowl, seemingly stable for eons, but capable of being knocked into a deeper pit. Quantum mechanics provides the knock. Through a process called quantum tunneling, there is a tiny, non-zero probability that a bubble of the true, lower energy vacuum could spontaneously form somewhere in space. This bubble would then expand at nearly the speed of light, its boundary a wall of unimaginable energy. Inside the bubble, the quantum fields would have reconfigured into their new, lower energy state. The laws of physics as we know them would cease to exist. Particles, forces, the constants of nature would be rewritten instantly. As the bubble wall rushed outward, it would erase our universe not with fire or ice, but with a transformation so complete that atoms, light, and time itself would be redefined. Our entire timeline would end not with a bang, but with a phase change, a cosmic reboot into a new reality with alien rules. The terrifying beauty of this idea is that it could happen at any moment, triggered by a random quantum event with no warning and no possibility of escape. It suggests our familiar cosmos is a temporary configuration, a local melody in the quantum fields that could, at any second, drop into a lower key, beginning a new song we cannot possibly hear. The profound instability of our cosmic foundations hints at an end. But what if that end is not a termination, but a transformation into a new beginning? Roger Penrose, the Nobel laureate who helped reveal the nature of black holes, offers a vision of eternity that rivals any myth. His conformal cyclic cosmology proposes that our universe is not the first, nor will it be the last. It is simply one eon in an infinite, unending chain. In this model, time has no true start or finish, only an endless cycle of rebirth on a scale so vast it redefines reality itself. The key lies in a mathematical trick called conformal rescaling, which allows you to stretch or shrink the geometry of spacetime without changing its shape. Picture a detailed map of an entire continent. If you shrink that map down to the size of a postage stamp, all the intricate details, the mountains and rivers, become compressed into an invisible point. But the relationships between them, the fundamental shape of the land, remains encoded in the map's geometry. Penrose applies this to the cosmos. In the far, far future of our eon, trillions upon trillions of years from now, the universe will be a cold, dark, and empty expanse. All matter will have decayed, all black holes will have evaporated via Hawking radiation, and only a sea of massless particles like photons and gravitons will remain, stretched to infinite wavelengths. In this bleak, featureless state, something remarkable happens. Because these particles have no mass, the concepts of distance and time lose all meaning. The infinite future of our universe becomes mathematically identical to the high-energy, ultra-dense singularity of a Big Bang. Through conformal rescaling, the end of time in one eon can be seamlessly attached to the beginning of time in the next. The postage stamp map of the dead future is expanded into a new, vibrant continent of a fresh cosmos. Our Big Bang was not a unique explosion from nothing. It was the conformal rebirth of a previous eon's silent end. This leads to Penrose's most controversial claim, evidence etched into the sky. He argues that when supermassive black holes from a previous eon evaporated in that era's distant future, their Hawking radiation released immense bursts of energy. This energy, he suggests, could have left faint, circular imprints on the fabric of spacetime. When that eon ended and transformed into our Big Bang, those imprints were stretched across the entire newborn universe, leaving ring-like patterns in the cosmic microwave background radiation, the afterglow of our own birth. While most cosmologists remain skeptical of this specific evidence, the theoretical possibility is breathtaking. It suggests information in some highly processed form might survive the transition between eons. The detailed history of a previous universe would be scrambled beyond any conceivable recovery, like a library burned to ash. But the ash itself, the total energy, and perhaps the quantum gravitational imprint of its most massive structures, could become the seeds for the next cosmos. In this sense, timelines achieve a form of cosmic reincarnation. The story of a galaxy in a past eon does not continue, but its fundamental essence, the energy of its conclusion, is recycled into the raw material for new stories, new laws, and new possibilities in the next cycle. Our entire history, from the first stars to the rise of civilization, might be built upon the silent, transformed echoes of a universe that came before. Penrose's vision gives us an eternity without a creator, a cycle without a cause. It asks us to see our fleeting moment not as a solitary spark in the dark, but as one brilliant flash in an infinite cosmic strobe, where every ending is a prelude written in the geometry of infinity itself. The very nature of probability is a gamble, but what if the gamble is not about the universe but entirely about you? Quantum Bayesianism, or QBism, offers a startlingly intimate interpretation. It proposes that the probabilities at the heart of quantum mechanics are not objective features of an external world. They are personal degrees of belief, a measure of your own uncertainty as you place bets on what you will experience next. In this view, quantum mechanics is not a description of reality out there. It is a personal guidebook, a set of rules for navigating and updating your expectations based on your interactions with the world. An agent, which could be you, a scientist, or even a simple detector, uses the quantum formalism to make better predictions about the outcomes of their experiments. The wave function is not a physical thing that collapses. It is a mathematical tool residing in the agent's head, a catalogue of their current beliefs about future experiences. When you perform a measurement and get a result, you do not collapse a universal wave. You simply update your own internal guidebook, your personal probabilities, to incorporate the new information. This radically reshapes the concept of a quantum timeline. There is no single objective history branching out there. Instead, your timeline is a deeply personal narrative, shaped stitch by stitch from your sequence of interactions and the expectations you bring to each moment. Two different agents can have perfectly valid but completely different quantum wave functions for the same system because they have different histories of interaction and different knowledge. Their realities, in a very real sense, are not the same. Consider the famous Schrödinger's cat scenario once more. For a QBist, the cat is not both alive and dead in some objective sense. Before you open the box, your personal wave function for the cat reflects your maximum uncertainty. You assign a 50% belief to the experience of seeing a live cat and 50% to seeing a dead one. The moment you open the box, you have a new experience. You update your beliefs instantly, setting one probability to 100% and the other to 0. The reality did not change out there. Your internal map of possibilities was simply corrected to match the territory you just encountered. This makes every observer the center of their own quantum universe. Your timeline is not a thread in a grand, pre-woven tapestry. It is a story you are writing through a continuous dialogue with existence, where each measurement is a question you ask, and each outcome is an answer that rewrites the next chapter. The spooky connections of entanglement are not mysterious links between distant particles. They are correlations in your expectations. If you know something about one entangled particle, you immediately update your beliefs about the other because your guidebook, the quantum rules, tells you they are linked. This interpretation dissolves the paradox of Wigner's friend, where one scientist inside a lab sees a definite result, while another outside describes the entire lab as in a superposition. For QBism, both are correct from their own perspectives. The friend inside has had an interaction and updated their personal wave function. Wigner outside, lacking that data, maintains a wave function reflecting his uncertainty about the entire lab. Neither has a God's-eye view of an objective reality because such a thing does not exist in the theory. There is only the interplay of individual agents and their experiences. So, what does this mean for the grand multiverse? In QBism, the many worlds are not physically real. They are expressions of the many possibilities you must entertain before you act. Your personal timeline forks only in your imagination as you consider what might happen before collapsing back into a single, lived experience the moment you engage with the world. It is a profoundly subjective cosmos where reality is not a stage we share, but a private performance shaped by the questions we dare to ask. The deeply personal reality of QBism rests on a sequence of experiences, one after another. But why does that sequence only run forward? Our most fundamental physical laws, from Newton to Einstein to quantum mechanics, are almost perfectly time-symmetric. They work just as well if you run the film backward, yet our lived reality is a one-way street. We remember the past, not the future. Eggs scramble but never unscramble. This irreversible direction is the arrow of time, and its origin is one of physics' greatest mysteries. The dominant answer lies not in the quantum rules themselves, but in the realm of thermodynamics, specifically in a quantity called entropy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. It is the reason heat flows from hot to cold, why perfume spreads in a room, and why your desk tends toward chaos. The arrow of time is the arrow of increasing entropy. But this raises a deeper puzzle. If the underlying laws are reversible, where does this irreversible increase come from? The answer points directly to the beginning of everything. Our universe started in a state of extraordinarily low entropy at the Big Bang. Think of it as a pristine, perfectly ordered deck of cards, all suits sorted and in sequence. From that improbable starting point, the only way to go was toward higher entropy, toward shuffling. Every process since, from nuclear fusion in stars to the chemical reactions in your brain, has been part of that grand cosmic shuffling, creating the forward flow of time we experience. Now we must connect this to the quantum world. How does a time-symmetric quantum process give rise to irreversible thermodynamic behavior? The bridge is quantum decoherence. When a quantum system interacts with its environment, its pure, coherent superposition decoheres into a mixed state. Information about the system's specific quantum correlations scatters into the environment, becoming practically impossible to recover. This loss of quantum information is an increase in entropy. The act of measurement, which forces a definite outcome, is a one-way ratchet. It takes a system of many possibilities and selects one, discarding the rest into the environmental noise, forever increasing the total disorder. So, at the quantum level, time symmetry is preserved in the full universal wave function. But for any localized observer like us, interacting with a tiny part of that whole, decoherence creates an effective statistical arrow. We only see the branch where entropy increases, because that is the only branch where memories can be reliably stored in stable, classical structures. This leads to a mind-bending speculation. If our arrow of time is a consequence of our universe's low entropy beginning, could other timelines or bubble universes have started differently? Could there be a cosmos where the initial condition was a state of maximum entropy, a perfectly shuffled deck? In such a universe, the statistical drive would be toward order, not disorder. For its inhabitants, time would appear to run backward from our perspective. They would remember the future and anticipate the past. A broken cup would spontaneously reassemble on the table. Light would converge into stars rather than radiating away. Their cause and effect would be reversed. To them, our universe would seem impossibly backward. While such a universe is mathematically possible, it is almost unimaginable for consciousness to arise within it. Complex, thinking beings require low entropy structures to store and process information, like brains or computers. A universe where time's arrow points toward increasing order from a disordered start might not allow for such complexity to form in the first place, so our forward-flowing time may be more than a local curiosity. It could be a prerequisite for existence itself, a necessary direction carved out by a single, quantum-fluctuated moment of exquisite order at the dawn of everything, setting all subsequent history on a one-way journey into ever greater, ever more interesting chaos. The relentless increase of entropy carves a single direction from the quantum haze, but how do we speak of a definite past when our theories only describe probabilities for the future? A 24th framework, the consistent histories interpretation, offers a powerful tool for doing just that, allowing us to reconstruct a coherent timeline from the quantum soup without needing an observer at every turn. This approach shifts the focus from instantaneous states to entire sequences of events, which it calls histories. A history is a specific, detailed story of what might have happened, a chain of events from the beginning to the end of a considered period. The key innovation is that not every possible story you can dream up is valid. The quantum formalism itself tells us which histories are consistent, meaning they can be assigned a sensible, non-contradictory probability without interfering with each other. Think of it like investigating a crime scene. You can propose many narratives, but only those where the clues do not contradict each other, where the footprint evidence aligns with the timeline from the security camera, form a consistent set. The quantum world works similarly. Out of the infinite number of potential pasts, only certain collections of events hang together in a logically coherent way, according to the mathematics of the wave function. In the famous double-slit experiment, for instance, there are two primary consistent history sets. In one framework, you can talk about the electron going through the left slit or the right slit as separate, consistent histories, each with its own probability. In another, equally valid framework, you can only discuss the electron as a wave that went through both slits and produced an interference pattern. Crucially, you cannot mix these frameworks within a single description. You cannot consistently say the electron took a definite path and also produced an interference pattern. Those histories would interfere and yield nonsense probabilities. The framework you choose depends on the questions you are asking. This is profoundly different from the many worlds interpretation. In many worlds, every possible outcome is realized in some branch. In consistent histories, we are not saying all these possibilities are physically real. We are saying that, given a particular way of analyzing the system, only certain stories make logical sense and can be assigned a probability. It is a calculus of meaningful narratives. This provides a powerful way to discuss the universe's own history without invoking a mysterious collapse or a continuous observer. We can apply a consistent histories framework to the cosmos as a whole, asking questions like, did the solar system form from a specific cloud of gas? The mathematics may show that histories where it formed from that cloud are highly probable and consistent, while histories where it spontaneously assembled yesterday are inconsistent or have vanishing probability. It allows us to carve out a set of possible coherent timelines from the underlying quantum blur. Our experienced reality, then, is not just one random branch. It is one narrative thread from a set of mutually consistent stories that the universe's own laws deem tellable. The past becomes not a fixed record, but the most robust and consistent story we can tell based on the present evidence, a story woven from the few threads in the quantum tapestry that do not tangle and contradict each other. It suggests that reality, at its core, might be less about what is and more about what stories can be consistently told. Consistent histories provide a way to tell a sensible story about our past, but what if the very stage for that story, the fabric of spacetime, is itself a story we are telling? Theory 25 pushes this idea to its ultimate limit. Spacetime may not be fundamental. It could be an illusion, a collective behavior that emerges from something far simpler and more bizarre, a concept explored in models like quantum gravity. Imagine the birth of the cosmos not as an explosion in a void, but as a network of pure potential. Every single possible thing is connected to every other possible thing. This is a complete graph, a state of maximum connection and chaos, where notions of distance and separation are meaningless. In this frenzied primordial state, the universe is hot and dense with relational energy. As it expands and cools, a phase transition occurs akin to water freezing into ice. The connections or links between these fundamental quantum bits begin to break. They do not vanish randomly, but in a pattern that crystallizes a stable structure. Most links freeze into a dormant, low-energy state, effectively turning off. The remaining active links form a stable, rigid lattice, and this lattice is what we perceive as three-dimensional space. The points where links meet become the locations of events, and the pattern of connections defines the geometry between them. In this view, a meter is not a fundamental unit. It is a count of how many links you must traverse between 2 points on the frozen graph. Time itself might emerge from the sequential changing of patterns on this graph, like the ticking of a cosmic clock as the network updates its configuration. This leads to a staggering speculation about timelines. The specific way the graph freezes is a quantum choice. Different patterns of broken and active links would create entirely different emergent geometries. One freezing pattern might yield our familiar 3 spatial dimensions and a forward-flowing time. Another pattern could freeze into a universe with 4 macroscopic spatial dimensions or 2, or a geometry where time behaves in a loop. Each distinct freezing creates a completely different cosmic arena with its own laws of physics, born from the same underlying quantum relational substrate. Our entire history, from the first stars to the rise of civilizations, would be a movie playing out on one specific frozen crystal of spacetime. Countless other crystals with alien geometries and impossible physics exist as other possible freeze-outs from that initial hot graph. This means the quantum timeline of our universe is not just one path through a landscape of possibilities. It is the unique history allowed by the specific frozen stage upon which we stand. A different stage would permit a completely different play with different actors and different rules. The search for a theory of quantum gravity becomes the search for the rules that govern how the graph freezes, the cosmic choreography that turns a blur of pure connection into the stable, familiar theater of our existence. The frozen lattice of spacetime might seem permanent, but there are places where it shatters completely. At the heart of a black hole, our understanding of reality breaks down at the singularity, a point of infinite density where Einstein's equations fail. This cosmic dead end creates one of the most vexing problems in physics, the black hole information paradox. Yet from this crisis emerges a theory of breathtaking cosmic fertility. The black hole final state proposal offers a radical solution, suggesting that the singularity is not an end but a gateway. Stephen Hawking's work showed that black holes are not truly black. They slowly evaporate, radiating away their mass over eons through a quantum process at their event horizons. This Hawking radiation appears to be completely random, carrying no information about what fell in. If the black hole evaporates entirely, all the detailed quantum information about the stars, planets, or books that formed it would be lost forever. This violates a sacred principle of quantum mechanics, unitarity, which states that information can never be destroyed. It can be scrambled but never erased. The paradox pits quantum theory against general relativity in a fight to the death. The final state proposal, championed by physicists like Leonard Susskind and later refined by others, makes a daring claim. Information is not lost because it never actually reaches the classical singularity. Instead, the proposal reimagines the singularity as a quantum boundary condition, a kind of cosmic firewall programmed with a specific rule. As matter and information plunge toward their doom, they encounter this quantum boundary at the final moment. The rule is this: anything that hits this boundary must be in a particular, preordained quantum state. Think of it as a cosmic bouncer at the door of oblivion demanding a specific password. This forces a profound interaction. The incoming quantum information, in all its complexity, must be reflected or transformed to match that required final state. In the violent process of matching, the information is not annihilated. It is scrambled and encoded onto the very structure of the quantum boundary itself. It is like throwing a magnificent, intricate stained glass window at a wall made of prisms. The window shatters, but the pattern of its colors and shapes is imprinted onto the light passing through the prisms, transformed into a new, brilliant spectrum. Here is where the timeline branches in the most literal sense. The proposal suggests this encoded information does not stay trapped. The quantum boundary, the transformed singularity, acts as a bridge. On one side is our universe with the black hole's event horizon. On the other side, the encoded information becomes the seed for an entirely new region of spacetime with its own laws and dimensions. In essence, every black hole is a big bang for a baby universe. The interior of a black hole in our cosmos does not end in a point. It expands out into its own separate reality, forever disconnected from our own. The implications for the flow of time and causality are staggering. From our external perspective in the parent universe, time for an object falling into a black hole seems to slow to a halt at the event horizon before it fades from view. Its information is conserved on the horizon's surface, as suggested by the holographic principle, and is slowly leaked back out via Hawking radiation over countless eons. But from the perspective of the falling object itself, it passes the horizon and continues inward, meeting the quantum boundary. In that instant, its timeline is severed from ours and grafted onto a new cosmic story. You could think of our universe as a great tree. Black holes are not dead knots in the wood. They are buds from which entirely new branches of reality grow, each with its own arrow of time and its own history beginning from that moment of quantum rebirth. This means the night sky is not just a collection of dark tombs. It is a nursery. Every supermassive black hole at the heart of a galaxy, every stellar remnant silently drifting in the void, could contain an entire cosmos within it, blossoming from the quantum information of everything it ever consumed. Our own universe might itself be the interior of a black hole born in a higher dimensional parent cosmos, part of an infinite fractal of spawning realities. In this vision, information is the ultimate immortal substance, never dying, but crossing a quantum threshold to be rewritten as the fundamental laws of a new world. The death of a star in our sky could be the first sunrise in another. The notion of a universe where every black hole births a new cosmos suggests a profound, hidden order behind creation. But what if that order is so absolute it leaves no room for chance, choice, or even the quantum randomness we have come to expect? This is the controversial territory of superdeterminism, a theory that dares to challenge the very notion of free will at the quantum level. It begins by confronting the most famous argument against hidden variables, Bell's theorem. In the 1960s, physicist John Bell devised a mathematical test to determine whether the weird correlations of entangled particles could be explained by local hidden variables, properties the particles carry with them from the moment they are created. Experiments have consistently shown that these correlations violate Bell's inequalities, seemingly proving that no local hidden variable theory can match quantum mechanics. The standard conclusion is that reality is either non-local with spooky action at a distance or fundamentally random. Superdeterminism offers a third, startling path. It suggests that the hidden variables do exist, but they are not just properties of the particles. They are properties of the entire experimental setup, including the physicist's brain, the settings of the measuring devices, and the particles themselves, all linked from the very beginning of the universe. In this view, the experimenter''s choice of which measurement to perform on an entangled particle is not a free, independent decision. It is itself predetermined by the same hidden variables that determine the particle's state. The correlation between the particle's behavior and the detector setting is not evidence of spooky action. It is evidence of a cosmic conspiracy, a pre-established harmony woven into the initial conditions of reality. Imagine two dancers who have rehearsed a single, intricate routine for their entire lives. When they meet on stage, their movements are perfectly synchronized, not because they send instant signals to each other, but because their entire history led them to this moment. From the audience's perspective, it looks like magic. From the dancer's predetermined timeline, it is simply the only possible outcome. Superdeterminism applies this logic to every quantum experiment. The reason entangled particles match each other no matter the distance is not because they communicate. It is because the universe, in its first instant, set up both the particles and all future measurements to be in perfect, locked step. There is no faster than light signaling because there is no signaling at all. Only a single, unbroken chain of cause and effect stretching from the Big Bang to this very moment. The implications for our understanding of reality are absolute and, for many, deeply unsettling. If superdeterminism is true, then the entire quantum timeline is not a tapestry of branching possibilities. It is a single, immutable thread. Every quantum event, from the decay of a radioactive atom to the firing of a neuron in your brain, was determined at the dawn of time. The universe is a cosmic film reel, and we are merely watching it play out. This eliminates the need for many worlds, for collapses, or for any true randomness. Probability becomes an illusion born of our ignorance of the ultimate, hidden variables. Free will, in any meaningful sense, vanishes. Your feeling of making a choice is just the experience of living through the one and only sequence of events that was ever possible. Proponents argue this is the ultimate in elegant realism, restoring a clockwork universe where everything has a definite cause. Critics, however, see it as a philosophical dead end that makes science itself impossible. If the experimenter's choices are predetermined by the same variables they are trying to measure, then scientific experimentation becomes a self-fulfilling prophecy, incapable of uncovering objective truths about an independent world. It is a theory that solves quantum weirdness by proposing a universe so rigidly interconnected that freedom, chance, and even discovery might be nothing more than poignant illusions in a story whose ending was written before the first star ignited. Superdeterminism locks every moment into a single, unbreakable chain. Yet a 28th theory reveals that the simple act of looking might not just reveal reality, but actively prevent it from changing at all. This is the quantum Zeno effect, a phenomenon where relentless observation can literally freeze a quantum system in time. It is named after the ancient Greek philosopher Zeno, who proposed paradoxes about motion, like an arrow that never reaches its target because it must first cover half the remaining distance, then half again, ad infinitum. In the quantum world, a similar stasis emerges from the mathematics of measurement. Consider an unstable particle, like a radioactive atom poised to decay. Left unobserved, it has a certain probability of decaying within a given second. But if you continuously measure it, checking its state again and again in rapid succession, something astonishing happens. The probability of it decaying during that period plummets towards zero. The watched pot, in quantum terms, truly never boils. The explanation lies in the collapse of the wave function. Each measurement forces the system to reset, projecting it back into its initial, undecayed state. With measurements coming in a relentless barrage, the system gets no chance to evolve naturally toward decay. It is trapped in a quantum version of a stutter, perpetually restarting its internal clock. From the particle's perspective, time itself seems to freeze. Its internal quantum processes, which would normally tick toward a transformation, are arrested by the external gaze. This is more than a laboratory curiosity. It has been demonstrated with atoms prevented from transitioning between energy states by frequent laser probing. The universe appears to grant a strange power to observation, the power to suspend change. This leads to a wild, speculative leap. If a civilization mastered measurement technology of unimaginable precision and speed, could it use the quantum Zeno effect on a macroscopic scale? Could they, in principle, lock an entire region of space, a planet, or even a star, into a single quantum state, freezing it in a timeless stasis? They would not be stopping time in the classical sense, but preventing any quantum evolution within that volume, halting all chemical, nuclear, and potentially even gravitational processes that rely on quantum transitions at their core. Such beings would not be mere observers of the multiverse. They would be its editors, capable of stabilizing precarious quantum timelines that might otherwise decohere or branch into chaos. Imagine a cosmic historian finding a rare, beautiful timeline on the verge of a catastrophic quantum fluctuation that would erase a galactic civilization. By subjecting that entire region of spacetime to a continuous, universe-spanning measurement field, they could effectively pin that timeline in place, preventing the fluctuation and preserving that history forever. It would be a form of conservation far beyond anything we can conceive, using the fundamental rules of quantum mechanics to create museums of reality. Of course, this is a staggering feat of engineering, requiring energy and control over nature that borders on the divine, but the principle is etched into the fabric of reality. Observation is not a passive act, it is an intervention, and in the right hands or the right instruments, that intervention might hold the power to silence the quantum tick of the clock, creating islands of eternal now in the flowing river of time. The power to freeze time with observation hints at a profound instability in reality itself. Yet a far more unsettling possibility emerges not from how we look at the universe, but from the silent, statistical churn of eternity. In a cosmos that is either infinite in space or eternal in time, the laws of probability guarantee that every possible configuration of matter, no matter how improbable, will eventually occur by random chance. Given enough time, a monkey typing randomly will produce the complete works of Shakespeare. Given enough universe, a random quantum fluctuation in the void will spontaneously assemble a perfect replica of the Mona Lisa. And given enough of either, that same random fluctuation could assemble something far more specific, a fully formed, conscious human brain, complete with all its intricate neural pathways, floating alone in the endless dark. This is the Boltzmann brain paradox, a thought experiment that uses our own physics to question everything we think we know. Named for the 19th century physicist Ludwig Boltzmann, who pioneered statistical mechanics, the paradox arises from a simple statistical truth. In a system that has reached maximum entropy, a state of total equilibrium and disorder, tiny fluctuations away from that equilibrium will still occur. Most are minor, a few atoms clustering together for an instant, but given an infinite amount of time, even the most wildly improbable fluctuation, like the spontaneous assembly of a complex thinking brain, is not just possible, it is inevitable. In fact, in an eternal universe, such freak fluctuations would happen an infinite number of times. Now, consider what such a brain would experience. It would pop into existence with a fully structured, functioning mind. It would possess what felt like a lifetime of memories of a childhood, of learning, of watching videos about quantum physics. It would have the sensation of a body, of a world around it, all generated by the intricate, false neural patterns formed in that single, random instant. To this brain, its reality would feel as rich and coherent as yours does right now. It would believe in its own past, in the laws of physics, in the universe it remembers. And then, a moment later, as the fluctuation subsides, it would dissolve back into the featureless void, its entire existence a brief, convincing dream in the cosmic noise. This leads to the paralyzing statistical conclusion. In an eternal or infinitely large multiverse, the number of these random, self-aware fluctuations, these Boltzmann brains, would vastly, overwhelmingly outnumber the number of conscious beings who arose the ordinary way, through billions of years of evolution in an ordered universe like ours. If you are a random conscious observer plucked from the ensemble of all possible observers, you are astronomically more likely to be a fleeting Boltzmann brain than a being with a real, continuous history. Therefore, the most probable explanation for your current feeling of consciousness is not that you are the product of a long cosmic evolution. It is that you are a statistical accident, a ghost thought that just flickered into being a moment ago, armed with a complete but entirely fictional past. Our entire shared history from the Big Bang to this sentence could be a detailed, coherent, yet utterly false memory. The planet you recall, the people you love, the laws of physics you trust, all could be an elaborate illusion generated by a random quantum event in an otherwise dead and empty eternity. This is not a claim that we are such brains. It is a logical paradox that screams something is wrong with our assumptions. Physicists see it as a powerful reductio ad absurdum argument against certain models of an eternal, featureless universe. If such a model predicts that most observers are Boltzmann brains, and we clearly are not, then that model is likely flawed. It becomes a guiding principle, steering cosmology away from theories that make our ordered existence wildly improbable. The Boltzmann brain paradox forces a brutal confrontation with the nature of evidence. How can you prove your memories are real? How can you trust that the past you remember actually happened? You cannot. You can only rely on the consistency and simplicity of the story. The universe we observe is ordered, complex, and obeys simple, elegant laws from its beginning. A single Boltzmann brain is an island of immense complexity arising from maximum disorder, a far more contrived and improbable specific event than the gradual unfolding of a low-entropy cosmos. So, while the statistics of eternity are terrifying, the most rational bet is that we are part of the coherent, evolving story, not the random static. Yet the paradox shadow remains, a chilling whisper from the void that our certainty is built on sand, and that reality itself might be the most convincing dream a random universe ever had. The final theory brings us full circle back to the observer, but with a responsibility that is nothing short of cosmic. John Wheeler's participatory anthropic principle proposes that we are not just passive witnesses to a pre-existing universe. We are essential participants in its very creation, bringing it into tangible being through the act of asking questions and making measurements. In this vision, the universe is a self-excited circuit, a grand loop where observers arise from the cosmos and, in turn, use their observations to solidify the cosmos that birthed them. It is a participatory democracy of reality, where every act of looking casts a vote for what is real. Wheeler took the delayed choice experiment, where a photon's past is shaped by a future measurement, and projected it onto the canvas of the entire cosmos. Imagine a quasar, a brilliant beacon of light from a galaxy billions of light-years away. Its light has traveled through the universe for eons, and on its way, it passed by a massive galaxy whose gravity acts as a lens, bending the light and creating multiple paths to Earth. We can choose today how to observe that ancient light. If we set up our telescope to detect which specific path the photon took around the gravitational lens, we force it to have taken one definite path, behaving like a particle. But if we choose to recombine the light from all paths, we see an interference pattern, meaning the photon came as a wave, taking all routes simultaneously. Our choice, made now in the present, determines what that photon was doing billions of years ago, long before Earth even existed. The implication is staggering. Our observations in the present could be retroactively determining the nature of quantum events at the dawn of time, pinning down possibilities that have remained in a ghostly superposition since the Big Bang. The universe did not simply unfold in a linear fashion. It waited in a state of potential for observers to emerge and, through their acts of inquiry, crystallize its history. This turns the entire quantum timeline into a story co-authored by its own characters. We are not reading a book that was written long ago. We are writing the book with every experiment, every glance at the stars, every moment we seek to understand. The universe needed us to become what it is. It is a thought that marries profound humility with unimaginable power. We are tiny and fleeting, yet our consciousness is the tool the cosmos uses to know itself, to transition from a realm of shimmering potential into a world of concrete fact. From the infinite branches of the many worlds to the frozen block of eternalism, from the bubbling multiverse to the holographic projection, every theory we have explored finds a strange unity here. They are all possible descriptions of the self-excited circuit, the grand loop where reality is both the question and the answer, the dream and the dreamer. The journey through these 30 theories is not just a tour of abstract physics. It is an invitation to see your own place in the cosmos anew. You are not a stranger in a strange land. You are a necessary part of its most fundamental machinery, a participant in the greatest story ever told. The story of how something comes from nothing and how that something learns to tell its own tale. From the infinite branching of worlds to the silent geometry of a timeless block, this journey has taken us to the very edge of human understanding. These 30 theories are not idle fantasies. They are the disciplined, daring work of generations of physicists, mathematicians, and philosophers, all wrestling with the same profound puzzle. Each one is a different lens, ground and polished by logic and mathematics, through which we try to glimpse the true face of reality. Some may be proven right, others may fade into history, but all of them represent our species' relentless drive to know. They show us that the universe is far stranger, more vast, and more interconnected than our everyday senses could ever suggest. To ponder these ideas is to exercise the most human of muscles, our imagination, while also practicing the most vital of virtues, humility. It reminds us that we are part of a mystery so grand that our very attempts to solve it become new chapters in its story. So, which of these visions of quantum timelines resonates most deeply with you? Does the participatory universe call to you, or does the cosmic certainty of a single woven block feel more true? Share your thoughts and questions in the comments below. If exploring the fundamental fabric of existence lights up your mind, be sure to subscribe. There are always more mysteries waiting just beyond the edge of the known.